Thank you guys for coming today. It's my pleasure to give you a lecture this afternoon. So I've been with the word prayer. Dear God, just thank you for this day, and thank you for the opportunity to come and learn about math and talk about it. Just help us have clear thoughts as we discuss affine spaces, and help you to not make a fool of myself. In Jesus' name, amen.
Amen. Of course, you can easily just not post this video, so.
True. But even before you. No.
But it seems like if you make a fool of yourself, the odds of me posting it are much higher.
Of course. That's all that I could expect.
Finally have my revenge.
So, today we're going to be discussing a fine topic.
Hey!
Thank you.
That was mine. That was mine.
Yes, we're going to be talking about affine spaces and simplexes and all that fine stuff. It's going to look a lot like a linear algebra class almost, but just with affine instead. So we're going to start out with a definition. We're going to define what an affine space is. So let's do it. So a subset A of Euclidean space is called fine if for all 2 points the line that goes through those 2 points is contained in A. Distinct points, that is. And you might wonder, well, that kind of sounds like how we defined convex space.
Mm-hmm.
But the difference is that convex talks about line segments, while affine spaces talks about the entire line.
Oh.
So for example, if you're looking at a disk would be convex since any 2 points you can do the segment between them.
Right.
But it's not affine because if you did the entire line,
So
it would not be contained.
affine implies convex?
Indeed it does.
Okay.
And it gives a few little specifications for special cases. The empty set and 1 point subsets are fine, I guess, trivially.
Mm-hmm.
And we start with a theorem that's, actually not.
You could just read it.
Yeah, it's pretty trivial. So if you have a family of convex or affine subsets of Rn, then their intersection is also convex or affine. And it's pretty easy to visualize. If you have 2 points in it, then they're both going to be in one of these subsets. So the line, yeah.
Okay.
And so when you're talking about a convex set, alright, so when you're talking about like a collection of points or just a subset of Rn, you can define the convex whole of that set, which is the intersection of all convex subsets of Rn containing that set. And wasn't quite sure if it's the same for affine spaces, so you can also define it like that. And so, yeah, so if you have a set X, the convex subset or the convex whole of that set will be denoted with these brackets. And so there's also kind of
This
explaining.
parenthetical remark is odd, right? Note that bracket X does exist for Rn itself as affine, hence convex. Huh.
So there is
there's an example of one, I guess.
yeah, there is a convex subset.
Okay.
There is a convex set that contains X. So
Yeah.
alright, and he's also kind of explaining why we're looking at that, because there's a lot of different kinds of convex sets, but with these you can actually kind of describe in general, like when you're looking at convex holes. Okay, so now I need a definition. I'll erase some of this.
Mm-hmm.
So now we're talking about affine combinations, which is very similar to linear combinations of a set of points. So an affine combination of a set of points in Rn set of n plus 1 points in Rn is going to be a point x of the form x equals t naught p naught plus t1 p1 plus tm pm with the sum of these di's being equal to 1. And a convex combination is an affine combination with each of these ti's being greater than or equal to 0.
Oh.
So for example, if you have 2 points,
Huh.
so the line between them can be represented. So x prime. The line between them can be represented as tx plus 1 minus t times x prime. But if you're wanting to restrict it to the line segment and not going past either of these lines, both of these have to be greater than 0. So the reason it's t and 1 minus t is because the sum of these is equal to 1, like we need to have for it to be an affine combination. Right. And then to make it a convex combination, you need to have, well, this needs to be greater than 0, so you need t greater than 0. And you also need 1 minus t greater than 0, which is why you define t on I.
I don't remember this. I don't think I did this in our previous discussions of these things.
Yeah,
I think we just looked at convex combinations back in the advanced calc class, right?
Yeah, we may have.
Cool.
Okay, so now we're going to do a fun proof. Take one, but I thought it was interesting. So basically, this. Let's see, I'll write down the theorem.
Yeah, you can erase all that. It's cool.
So this next theorem is actually showing that the convex whole.
You're welcome to write up in the corner too.
Okay.
You might want to give yourself room for the proof of this thing, right?
Yeah. So the convex whole of a set is of a set of points is precisely the set of all convex combinations of these points.
Ah. While you're writing, convex hull was the intersection of all convex subsets of Rn containing those points.
Yes, denoted with these brackets.
Right.
Is the set. So let's do some double containment. Okay, so he denotes this to be S. Okay, so the first thing we're doing is proving that the convex whole is a subset of S.
Alright.
So he says, it suffices to show that S is a convex set containing all of these points. Because the convex whole is the intersection of all of these such convex sets. So if S is one of these sets, then the intersection is obviously going to be a contained in it.
Okay.
So here we're looking at a set of points Okay, yeah, so the first thing he does is saying that, well, each of these points, we first want to start by saying that each of these points is an S.
All right.
And the way we can see that is like, for example, to show,
Yeah.
it's kind of silly, like
Sure.
P naught is equal to 1 times P naught plus 0 times P1. Okay, which is an element of S.
Okay.
We'll grade the same for all the other ones.
Okay.
And so now we're taking two. All right. So So now to show that S is convex, we're taking two elements of S and showing that the segment that between them is actually going to be contained in S. So let alpha equal to the sum of AI times PI, beta equal to the sum of BI times PI, both of which are in S. And so, right, since they're convex combinations, the sums are equal to 1, and each of these coefficients is greater than or equal to 0. Alright, so let's find so now we're trying to show that the line between these 2 points, T alpha plus 1 minus T beta,
Right.
is an element of S for all T and I. Okay? And so he writes it out as a sum, so he can say, using the definitions of alpha and beta, or the writing in terms of combination. Right. So you got T, so you can write it as the sum from I equals 0 to M of T AI plus 1 minus T BI, all that times BI.
Cool.
So basically, yeah, combining this and this. And so this is a convex combination because, what we want to show is that the sum of these coefficients is going to be equal to 1,
right,
and that each of them is greater than 0. So sum of T,
You're fine.
TAI
I'm
plus
just squeaky.
1 minus T BI is equal to, you can split up this sum,
Yeah.
T times sum of AI,
So you pull out the T and the 1 minus T.
right, plus
Yeah.
1 minus T times sum of BI, also 1, which is equal to T plus 1 minus T, otherwise known as 1. Okay, and then each of these is going to be greater than or equal to 0 because AI is greater than or equal to 0, BI is greater than or equal to 0, T is greater than or equal to 0 because T is an I,
Mm-hmm.
and 1 minus T is also greater than or equal to 0. So these are all going to be non-negative. And so thus S convex.
So you've shown the line segment between alpha and beta is again in S.
Mm-hmm. Which shows that S is convex, which shows that the convex whole is a subset of X. Okay, now the second one. Get to do some induction.
So there you're using that, you're assuming that the convex hull is a subset of S. How do you use that?
We're not assuming we're proving it.
Oh? Oh. So what are you assuming about S?
That it is the set of convex combinations of
Oh,
T's
okay,
equal to
okay,
0 to
okay.
PI, which is how we get like alpha and beta being elements of S.
I see. So the fact that alpha and beta are convex combinations
Of these
means
points means that they're elements of S.
that's by construction. That
By
means they're
construction,
elements of
exactly.
S.
Yeah, And the same with the line between them, or the points in the line between them. That's how we show that they're elements of S.
The fact that they are a convex combination gives them, makes them a member of S. Okay, okay, gotcha. And now for the other containment. I can hardly contain myself.
Okay, so now we're going to be doing
Sorry for that.
induction.
That was awful.
So,
Now that I'm not writing on the board, I have more time to think about puns.
so to show that S is a subset of the intersection of all convex sets containing these points, we have to show that S is a subset of X for all X containing these points. So we're going to do induction on M. And so we start out, okay, so for M equals 0, well, okay, so it's just 1 point, which is going to be equal to S, because any convex combination of P naught is going to be just P naught. It's going to be 1 times P naught. And actually, we already said that this is already a convex. The set of 1 point is just a convex. It's already convex, so we're good with that. Okay, so if we say, suppose it's true for M equals K. Okay, therefore, if so if you have K points, so like P K minus 1. Because, alas, he starts counting at 0. Actually, just kidding.
It's lonely over there, isn't it, Nathan?
I guess M isn't the number of points, so we don't need to. So this would be K plus 1 points. Okay.
And this book also starts counting at 0. It's got a chapter 0, right?
How dare he?
It's not natural.
So we suppose that if these points are on S, or not S, and some subset X, then S is a subset of X. Okay. And now, use the chair. Okay, so now we're looking at M equals K plus 1.
Daniel
So-
in the comfy chair. If only I had some soft cushions.
So now suppose that they're K plus 2 points, not necessarily the same ones, on some set, on some convex set containing, on some convex set S, okay? Sorry, X. Let's see it better. So the first thing it says, okay, so we can assume that, so we're looking at some point P that's an element of S. So P is equal to sum of Ti Pi with sum of Ti equal 1 and Ti greater than or equal to 0. For all I. I want to show P is an element of X. Okay. So what we do, so he says, so we can assume that T0 is different than 1, because otherwise P is just B naught, which is we know is an element of X. So they say, okay, so T naught different than 1. So we can find this new point Q, which is going to be equal to T1 over 1 minus T naught, P1 plus T2 over 1 minus T naught, P2 Tm, oh sorry, I changed a little bit from his proof. Tk plus 1 over 1 minus T naught, Tk plus 1. But if you look, P1, P2, that ends up being K points. all of which are in X. And so, and this is a convex combination.
Why isn't that k plus 1 points? I'm missing something.
I'm sorry, yeah, it's k plus 1. Yeah, so the number of points, yeah, you're right, it's k plus 1 points. Yeah, it's what happens when you start counting at 0.
Not even once.
Okay, right, so
So your induction hypothesis is that
if you have k plus 1 points, okay, I'll just write, yeah, k plus 1 points, then any convex combination of it is going to be an X. Okay, so here we actually have k plus 1 points, and we have a convex combination because if you take the sum of all of these, t1 plus t2 all the way to plus tk plus 1, that's going to be equal to 1 minus t naught. Because we assume that the sum of all of t naught plus t1 plus all of it is going to be equal to 1.
ah
So therefore, the sum of all these divided by 1 minus t naught,
sneaky convex.
and all of these are greater than or equal to 0. So therefore, Q is an element of X. Right? And then, since X is, let's see, I'll just move here, okay. So we know that P naught and Q are elements of X, and X is convex, therefore P, which is equal to T naught times P naught plus 1 minus T naught Q, from how we defined what Q is. Q is basically 1 minus P naught divided by 1 minus T naught. That is an element of the line between P naught and Q, which is going to be an element of X, because X is convex. Therefore, P an element of S implies P an element of X, therefore S is a subset of X for all X, containing these points. Yeah, and I think that's it. So, so that shows this other side of the containment. So, I'll erase all this now, so you guys got it down.
Yeah.
What?
Is corollary in a fine set spanned by these points. Oh, so basically you can take this theorem and
Yeah, and not assume that each of these TAIs is greater than or equal to 0, and you get the exact same result with affine.
I do think it's interesting though that he gives a notation for convex combinations.
But not one for affine.
Yeah,
It's
even though it's used like just as often.
Yeah, that's true. We gotta find a new notation. Alright, so now he talks about affine independence. Again, more of this, or affine independence, more of these parallels with Skinner's. So,
Right, yeah.
something like this
Notation.
instead of like this. Span,
yeah, we can do
convex span.
it. Let's do it. Next time it comes up, okay. So if you have ordered set P naught,
I bet he does that later anyway.
PM,
Let's skip ahead.
subset of Rn. Okay, so that's going to be denoted affine independent. If the set P1 minus P naught,
Cameraman is off for lunch.
P2 minus P naught, PM minus P naught is linear independent. Okay. So in the linear algebra sense. So he says that any linearly independent subset is also an affine independent set. Which seems pretty straightforward. But the converse isn't necessarily true, because you can take a linearly independent set and pair it with the origin, and just, therefore, each element of that linearly independent set minus the origin is still, going to make a linearly independent set. Therefore, the converse isn't true. And then he also looks at some special cases. Any one-point set is affine independent. Truly, and okay, and then it says, okay, so 2 points are going to be affine independent if they're not going to be the same thing, if their difference is different than 0. And with 3 points, it's going to be affine independent if they're not collinear, and then 4 points if they're not coplanar, etc. I'm not going to draw that one.
So the idea of affine independence is you can define the biggest space you'd expect in terms of just spanning and linear. I mean, like 3 points should determine a plane, 4 points a volume, 2 points a line, right?
Okay, so we got this theorem, which is going to be a TFAE.
I see.
The following are equivalent. Okay, so the first one is that this set, I'll just write it. PM is affine independent, which I will write as AI. Sorry, it's not computer stuff. And so, okay, now if you have this set of coefficients, all of which are in R, with the sum being equal to 0, okay, whoops. That is true, but first, if the sum of these coefficients times pi is equal to 0, and the sum of these coefficients is equal to 0, then all of these coefficients are actually going to be equal to 0. And the third one, now that we have this kind of like independent definition or property, we can talk about what do you call it? Uniqueness of coefficients. So each x element of A has a unique expression as a affine combination.
The ordering there is, of course, important.
Mm-hmm.
Yeah.
Yeah, we're always considering an ordered set
Yeah,
here with
yeah.
a affine.
As you will experience sometime soon when you teach Calculus 3, the order that you make the base point for the plane greatly influences the formulas that follow after.
Yes, exactly.
Yeah. But I think you can safely skip the proof of this one
Okay.
as to get to the...
Yeah, it's not. It's actually a pretty
I think
easy.
it's very similar in content to the one we just did.
How are we doing? I don't want to take too long. Obviously, I don't want to go over. Okay, I guess I should hurry up. Okay.
I just want to make sure you have time to talk about faces and such.
Yeah, I guess that's kind of what we're going for.
Yeah.
Right. So if you have this, then these TRs are going to be unique. If yeah, so these are all equivalent.
So-
Proof is pretty fun. I was looking forward to it.
Sorry. Sorry.
Okay, but one.
If we have time for it at the end.
Yeah, but actually,
Or does it matter?
you'll see that while ordering does matter with the expression, it doesn't.
Well, if you need to go over it. It's cool.
Yeah, no, it doesn't affect affine independence. So there's no like reason that P0 would have to come before P1 and whatnot, like especially here to show that this is affine independent. So that's what corollary 2.5 says.
Oh.
Okay, and another corollary that I'm not really going to go too much into is that an affine set in Rn spanned by an affine independent set, P0 through Pm, if that's an affine independent set, then A is actually a translate of an n-dimensional subvector space. So for example, if you have two affine independent points, they're not the same thing.
Yeah.
Well, this is actually just going to be a translate of what this vector space would be.
Right.
So vector space, yeah.
So basically, like a reordering, in some sense, these T's in your, or I guess S's, yeah, the S's you have in 2. No, wait a minute. Oh, I'm sorry, in 3. In 3, the T's you have, they're coordinates, really, with respect to the set P0 to P, whatever it was, N.
Yeah.
And if you reorder it, it's just changing coordinates, but it wouldn't change the affine independence.
Yeah, we'll even give a special name to these coordinates.
Ooh. Tell me more.
I'm not going to go into this stuff about general position because I didn't really see any more of it in the rest of the chapter. And it's like the theorem's interesting. It's interesting, but that's also like a weird argument with Van der Monde matrix, which I don't really know too much about. Alright, so now we can go to these coordinates that Dr. Cook was alluding to.
I think it was mostly you, but okay.
You're the one who first mentioned that. Or called them by what they really
Oh, I called them coordinates. Oh, I see.
I might have called them that.
I see coordinates everywhere, though.
Whoa. Okay, so if you have an affine independent subset, okay, it's always going to be affine independent from now on, I think. And A is the affine set spanned by this subset. Alright, let's do it. View. If X is an element of A, then there exists a unique m plus 1 tuple where X is going to be this combination of these points with these coefficients. Alright, so we already, like from the last theorem that I've proved, this is unique. And these are called I actually don't know how to pronounce this word. Barycentric? Yeah, barycentric coordinates.
Yeah, barycentric.
Barycentric.
I think what you said first was better.
Yeah.
I guess it's what it sounds like, barycentric. But, yeah. We should go ask Dr. Skibordis. No.
Yes.
Is it Greek? Sounds Greek.
Yeah, I think he talks about the origin of it. Yeah, from the Greek baros, meaning heavy. He's actually, the barycenter actually represents the center of gravity, but I'm getting ahead of myself. Okay, so, yay, simplex. So we got another definition.
What is he up to with his general position stuff?
I don't know.
I mean, it seems like he's
I mean, it's interesting, kind of. No,
It'll
some is
it'll
interesting.
it'll show up later somewhere.
Sure. We would do that. Okay.
I don't
So,
know.
Affine independent. Then the convex set spanned by these points is actually going to be called
Very good.
affine. If you want to say affine, this is not going to be necessary. M simplex with vertices P naught through PM. Okay. And once I prove this theorem and do another definition, I'll go into some examples. Actually, we'll go into examples now while we're at it. So, for example, if you have 2 points, the one simplex is just going to be the line segment connecting these 2 points. If you have 3 points, it's actually going to be the triangle. If you have 4 points, it's going to be the tetrahedron. All of these filled in.
5 points.
You can imagine it, I'm pretty sure.
A 120 cell or something. Forget what it's called.
Are they in general position?
If they're affine independent, they're in general.
General position if every n plus 1 of its points forms an affine. Sorry.
Okay, yeah. Theorem 2.8, there's not really too much to say about it. So if you have this M simplex, then the barycentric coordinates are unique. I think that's what it's saying. It's kind of, it's like barycentric coordinates were defined for an affine space, but it's pretty much the same thing for a convex one, as long as they're each greater than or equal to 0. Cool. Using what we had before, and then so also define the barycenter.
Mm-hmm.
The center of baries. Okay. Okay. I'm getting tired of writing this. PM. Define independent, then the barycenter of this simplex is. I did not like his notation here.
Oh, you talking about the parentheses?
Yes.
Yeah, I noticed the same thing.
I was like,
he actually does that a few times.
Yeah, I know. I was confused
It's really
for a few minutes, just trying to figure out like
It's-
where is it?
So it's 1 over m plus 1.
Yeah, he wrote
Yeah.
1 divided by m plus 1.
Yeah, I take off points for that.
With like parentheses here, which is yeah. Sorry. Come on, Robin, you can do better than that. Okay, but it's the sum of all these. So it's 1 over m plus 1 times the sum of all these. Okay, so for example, yeah, so like I said before, it actually represents the center of gravity of these simplexes. So for example, if you had like a piece of paper of a triangle and you set it on the on a needle, like on the barycenter,
Right.
in theory, stay balanced.
Assuming, of course, that the whatever. I guess. Well, we're filling out. It's funny. Are we thinking about point masses at the points, or are we thinking about like? We're not thinking. It's a triangular region, right? Yeah.
Yeah. Or if you threw it, it would rotate around.
Yeah. It's funny because like the formula from a physics perspective, it's center of mass, assuming that the mass is 1 at each one of the points, you know?
Yeah, assuming it's like uniformly
But
distributed.
geometrically you're thinking about like these, you know, areas or lines, right? So
So if you're looking at a line, the barycenter is actually just going to be the middle of the line.
yeah.
If you're looking at a triangle, I guess it depends. It's an equilateral triangle. It's not too hard to find it. It's just the.
But it's just I mean it's kind of, I guess it's kind of obvious, right? Like the the center of mass for a laminate is the same as the center of mass for its vertices, assuming that like equal mass at the vertices is the same as like a uniform distribution of mass. I mean,
so.
it's
Yeah, we're not in a physics
those
class,
are
guys.
really different things though. Sorry.
Yeah, sorry.
Yes, we are. I'm sorry. I'm bringing physics into this. My apologies. Excuse me.
I'll forgive you one day.
Take it back.
Case scenarios. Okay, and then in example 2.5, he talks about the standard M simplex, which is actually
Yes.
just going to be, so for example, if here are two standard M simplex is going to be the point, or the line between 1, 0 and 0, 1. Here in R3, it's going to be this triangle between 1, 0, 0.
So it's the convex hull of the
convex
standard
hull of
basis.
the standard basis. Yeah, okay, and so,
Cool.
okay, so now he goes into some terminology. I just realized I'm doing everything in the same color, sorry. about
Okay.
that. I don't know. Maybe one day I'll figure out how to balance all that. Actually, I don't know. That's not right. I think it's necessary. I guess I'll write it. Okay, so if you have an M simplex,
Defining the face
yeah. So the face
opposite.
some pi will be the M simplex, or the M minus 1 simplex of all points with pi thrown out. Okay. With yeah, and then he defines what that is. Okay, and then the boundary is going to be the union of all these faces. I'll write that down. Okay, and you can also talk about k faces of an M plus or an M simplex. So, for example, if you had a triangle, a 0 face would just be a point, I think. A 1 face would be one of the edges. And, well, it's already a 2 simplex, so 2 face would be the whole thing.
I think we discussed this before, but you should never tell your girlfriend that she's just got a K face.
Alright, and then some. How are we doing on time?
There's no time for us.
If there's a two-face, you have a Hillary Clinton.
Oh.
She's so dihedral. Oh, we have to vote for Trump or Hillary. I know, Johnson, but he doesn't know where Aleppo is, so what do you do about that?
How dare he?
Yeah, I know.
Okay, so. Alright, so now we got some.
99% people until then.
Yeah, really.
And
Exactly.
then afterwards,
most people have-
everyone got their PhD in Aleppo.
Right, everyone who watched that clip for the first time was like, what's that guy talking about? They'd be like, oh, how dare he. Yeah.
Okay, so now we're just talking about
Sorry.
properties of simplexes. And just like distances, pretty much, and various centers on simplexes. So, if you have 2 points, then the distance between them is going to be less than or equal to the supremum of the distances from u to the,
Ah.
I don't know,
Mhm.
yeah, sorry, u minus v, minus pi, okay. And the diameter of S, which I looked for like where else he talked about that and didn't find it, but it's the greatest possible distance between 2 points in it.
Yeah.
So it's like, why is this a theorem? But no. So it's actually going
So
to be
this is a definition.
pretty much, unless
Yeah.
he mentioned it somewhere I didn't see.
I guess the point is, the proof here is that because S is so constructed, the points are in there, and so like those are, I guess technically the primordial definition would be like all possible points in S, which include things other than just the
he
points.
He just reduces it to the boundary.
Right.
Yeah.
Yeah,
Yeah.
the boundary.
Or not even the boundary, just the
Just
points.
the
that
point.
The edges,
Yeah.
the edges tell all you need. Really need
Which
to know
happen-
Or
about
the
it.
zero faces.
The yes, the zero phases, which of course happen to be on the boundary. Yeah.
Okay, again, the messed up notation, but I'll fix it, don't worry.
Ah, how dare he?
Yeah, so the distance from the bare center to
Yeah,
any of these points is
I
going
would-
to be less than or equal to
I
the...
would definitely take out points in a Calc 2 test for that, for sure.
I was like, well, n over n, that's just 1, guys.
Yeah.
So, yeah, so it's going to be less than or equal to n over n plus 1 times the diameter of S, so... Not too
I guess it's
complicated.
just for the sake of, I mean, otherwise this calculation would be much bigger in terms of typesetting. You know? Like, there's that division by 1 over n plus 1. Oodles of places in here. If you went to fraction notation,
At least add like 2 parentheses.
there'd be a lot of parentheses too. Like, yes, but
Yeah,
then it
people
would be,
get over it. I mean, this guy, well, Rotman, when was this written? I guess relatively recently. 1988. That's usable.
I think this is the...
Like, he started with 0, so he probably has some connection to theoretical computer science. So he's probably seen Lisp before. So like, he should use as many parentheses as is possible.
Gosh.
Cool.
Computer science is your Berry Center. It's here.
Alright, so we got
That's an
B
insult, by the
is
way.
a convex combination, because it's in simplex. Therefore, the sum of TI's is equal to 1. So, rewrite V as sum of TI PI. Rewrite U as sum of TI times U,
Mhm.
because sum of TI is 1. Then you can use triangle inequality, pull out the sum of TI's. So sum of TI times its distances. Each of these distances is less than or equal to the supremum, obviously, and then sum of TI is equal to 1.
Cool.
So,
Man, I think I just found some future advanced calculus homework right here.
2's even better. Just repeat the process.
Huh.
Right, so with PI, with PI being the U instead, it's going
Mhm.
to be the less than or equal to the supremum
Hmm.
over J of PJ minus PI. So, yeah, so the greatest possible distance between like 2 points is going to be less than or equal to the greatest possible distance from one of the points with the supremum of one of the points with the edges, which is less than or equal to the supremum of 2 different, not edges, vertices, sorry. Okay, and then bare center. You guys want to do the bare center or not? Yeah, we can do the bare center.
Yeah, I think you got time for it.
Okay, so reminder of what the bare center is. B is equal to 1 over n plus 1,
Heavy man.
sum of pi. So B minus pi, distance from B to pi, is equal to distance from sum of 1 over n plus 1 pj minus pi. Summing over j. Which is equal to this j equals 0 to n of bj minus because the sum of these is actually just going to be equal to 1. 'Cause it's, 1 plus 1, n plus 1 times. So we can rewrite pi as this. Before. Oh well, what did I do? Okay. Which is equal to the sum of 1 over n plus 1 times pi minus pj, or pj minus pi, which is less than or equal to 1 over n plus 1.
So this gives us an explicit relationship between the diameter of the n simplex
And the Baire curve gives us like an estimation of how far the Baire center is from each point, or
from the vertices of the
for each of the vertices.
Hmm.
Which, okay, so this is just oh right, okay, so that's
Hmm.
less than or equal to n over n plus 1. Actually, I'll show you the supremum of the greatest distance between two vertices.
Mm-hmm.
Okay, and so the reason it's this is because this is less than or equal to, well, each of these is less than or equal to the supremum,
So you
and
just
actually one of them is equal to 0. So that's why you end up having a sum of n. If you just wanted to say, okay, well, each of these less than or equal to the supremum, you'd end up summing over n
n
plus
plus
1.
1.
But you take one off because one of them's always going to be equal to 0.
I see.
It's
I didn't notice that some
one.
started at 0. I didn't understand that to start with, but I
Mhm.
gotcha.
Which is equal to
The diameter.
n over n plus 1 times the diameter.
Huh, cool. It's fun to think about what that means for like a triangle.
Yeah, because it's like, I remember learning that like with an equilateral triangle, the center of gravity, like center of pretty much everything for an equilateral triangle, like the distance from that to each of the vertices is a 2/3 of the length of each side,
Huh.
which is precisely like what this shows.
Huh.
Yeah, so it's like confirmed.
Because you got 2.
So the bound is sharp for an equilateral triangle.
Wait,
Yeah,
so
exactly, yeah.
so
I imagine it's probably sharp for like any regular.
Yeah, that would make sense.
The wait. So the triangle again was a what simplex?
2.
Yeah, 2 simplex.
Right.
Oh right, 'cause it's 2-dimensional.
Mm-hmm.
Yeah, 2/3. Okay, cool. Yeah.
Alright, and now to finish off the comparisons with linear algebra, we're going to be talking about affine transformations.
I imagine the proof that that's sharp for regular. I guess you could talk about a regular simplex,
Yeah.
like a generalization of a regular, like equilateral triangle, an equilateral, like a tetrahedron, an enhedron.
Yeah, how would you define that?
So the distance between each points is the same.
So the proof that what you just did is sharp in n dimensions for such a thing.
Well, if each of the distances is the same thing, then
You could probably just
it's probably not that hard.
look at the integral, like average all the points, see what it works out to. I don't know, n-dimensional integral, that might be. Maybe you could use,
right.
maybe
right,
you could
right.
use induction somehow on the iterated integrals. I don't know.
So that brings us to affine
Affine
maps.
Yep. Affine transformations.
What a fine map.
What a fine map to look at.
A fundamental groupoid emerges. Not yet.
Okay, so this is the affine set that it spans. So the affine map T from A to RK is a function, or unaffine map that is. T of any combination of the vertices, or of these points, is going to be the affine combination of t of each point. Whenever, right, so affine combination, so if ti is equal to 1, or tj equal to 1. And the restriction of t to the simplex, the M simplex, span with its points, is also called the affine map. A little let down.
Huh. I'd think it would be a convex map, but you'd be wrong. Okay.
Okay, so it says affine maps preserve affine combinations and hence convex combinations. And the uniqueness of barycentric coordinates allows this to be well defined. Because if it weren't, then yeah, you'd have some issues. Okay, and then we got our final theorem. If PM is an M simplex, and we have our N simplex, Q naught, Qn, Q. And we have some function mapping the vertices
Bad cameraman.
to the simplex, to the second simplex. Then there exists a unique affine map T from the entire simplex. And by P naught through Tm to the simplex. With T of Pi is equal to F of Pi. So basically you have you can create an affine extension where it's actually defined the entire simplex. And so the proof of that is, well, you can just define T by T of any convex combination, because we're on simplexes, is equal to sum of Ti F of Pi. Where any point, so any point is any like convex combination, which is an element of the M simplex. And so you can check that like T of Pi is going to be equal to T of like 1 times Pi, plus 0 times everything else, which is just going to be F of Pi, which is what we want. And
Uniqueness.
I guess we could try to prove that.
I think
I guess
we
that's
also
from
wanna
the barycentric coordinates.
Right.
You can use the uniqueness of that. I think.
yeah, you have a formula in terms of barycentric coordinates, so that's unique. I think that's the argument.
Right.
I mean,
yeah,
you could
coordinates.
you could assume. I suppose you could assume you had a sum over Ti prime F of Pi, and then you set them equal, and then you get Ti equal to Ti prime. Ooh, same thing. But again, like you said, Nathan, it's the uniqueness. I'm sorry, uniqueness is visible.
Yes.
Obvious.
Obvious. So let's see. So we have.
I used visibly in my abstract notes I was writing yesterday.
Do you guys believe this in a affine map?
I didn't use this too much.